So, what's the real secret sauce behind models like GPT-4? It's not just hype. It's actually a single, beautiful piece of math. Today, we're going to pull back the curtain on the one formula that really kicked off the entire modern AI revolution.
And this is it. This is the formula. It's called scaled dot product attention. Now, I know it might look a little intimidating. You've got these letters, a square root, something called Softmax, but this one equation, it's the engine inside the transformer architecture, which is the foundation for pretty much every major AI breakthrough we've seen in the last few years.
And trust me, that is not an exaggeration. See, before this formula came along, AI had this massive memory problem. So to really get why this equation was such a game changer, we first need to understand the huge roadblock it was built to completely demolish. To really appreciate the solution, you have to feel the pain of the problem it solved. For years, AI models that worked with language, or really any kind of sequence, had a major weakness, kind of like a really bad case of short-term memory loss. The old-school models were called recurrent neural networks, or RNNs. And they processed information one piece at a time, sequentially, like you or I would read a book word by word. The issue was, by the time an RNN got to the end of a long paragraph, it had basically forgotten what was said at the beginning. The context just faded away. It couldn't figure out that the word "it" at the end of a long story was referring to the robot mentioned way back on page 1. And this was a huge, huge problem. So, to fix this memory issue, researchers came up with this brilliant concept called attention. And you know what? The best way to wrap your head around it is with an analogy we all use every single day: a search engine. Or maybe a better way to think about it is a super fast library retrieval system. Okay, first up, we have the query, which we call Q. This is what the model is focused on right now. Think of it exactly like the search term you type into Google. It's the question the model is asking itself, like, hey, what information is most relevant to this specific word I'm looking at? Next, you've got the keys, represented by K. Think of these as all the titles, all the keywords, or the labels on every single file folder in the library. The model takes its query and compares it against all of these keys to see which ones are the best match. And finally, we have the values, or V. This is the actual stuff inside the file folders, the rich information that's associated with each key. Once the query finds the right keys, the model pulls out their matching values. So it's really simple, right? You ask a query, you scan the keys for a match, and you pull out the value. All right, with that query, key, and value idea locked in our minds, let's go back to that scary-looking formula and see how it pulls off this exact process with just incredible efficiency. This whole process maps perfectly to our library analogy. So step 1 is all about measuring similarity. The model does a dot product to compare every single query with every single key, which spits out a relevant score. Step 2 is scaling, a super important stabilizing step we'll talk about in a second. Then, in step 3, this Softmax function takes all those raw scores and turns them into clean percentages that all add up to 100. This is literally the model deciding how much attention to give each word. And finally, step 4, it multiplies those attention percentages by the values, and out comes a brand new context-rich version of the original word. Okay, let's zoom in on that one little part, that division by the square root of d sub k. Now, that dk just stands for the dimension, or the size, of our key vectors. Simple as that. This little piece of math looks like a minor detail, but it is absolutely essential for making these giant models learn anything at all. Here's the deal. Those dot product scores can get really big really fast. And when you feed giant numbers into that softmax function, it kind of freaks out. It gets pushed to its extremes, becoming way too confident and assigning like 100% importance to one thing and 0 to everything else. When that happens, the signals the model uses to learn, called gradients, they just shrink down to nothing, and the whole learning process grinds to a halt. You can really see the effect right here. Without scaling, the model is basically shouting, it's 99% this one word and nothing else matters. It gets way too certain and the learning just stalls. But by scaling those scores down first, we get a much softer, more reasonable distribution of probabilities. This keeps the whole learning process stable and lets the model find all the interesting nuances instead of just jumping to crazy conclusions. So we've got it. Attention solves the memory problem, and scaling makes it trainable. But the biggest breakthrough of all, the reason this formula is absolutely everywhere, it all comes down to one thing: speed. And I'm talking about mind-blowing, revolutionary speed. To see why, let's put them side by side.
Remember how those old RNNs had to crawl through text one word at a time? It's fundamentally slow. You can't process the 10th word until you've already dealt with the 9th. Well, attention just throws that whole idea out the window. Its main calculation compares every word to every other word all at the same time. It's not sequential, it's massively parallel. And this completely unlocked the power of modern hardware, like GPUs, which are literally built for this kind of parallel number crunching. It meant we could suddenly train models on way more data, making them way more powerful in just a fraction of the time. This wasn't just a small improvement, it was a total paradigm shift. So the next time you see a large language model do something that seems like pure magic, just remember what's really happening under the hood. It's not magic. It's this incredibly smart but understandable system of asking questions, checking for relevance, and retrieving information, all through a giant parallel network of queries, keys, and values. And it all comes right back to this, a formula that I hope looks a whole lot less intimidating now. It's really just a recipe for finding relationships, for understanding context, and for doing it all at a scale and speed that was pretty much unimaginable just a few short years ago. These few symbols have truly reshaped our world. This one solved the problems of memory and speed, and that's what unleashed the AI boom we're living in right now. And that leaves us with one last really exciting question to think about. What's the next huge roadblock out there, just waiting for its own elegant, revolutionary formula to come along and crack it wide open?